Welcome to the Explainer. Let's just jump right into this. At first glance, the rigid rules of measurement might sound like the absolute driest topic in all of science. But today, we're taking those rules and transforming them into exactly what they are: a powerful, dynamic toolkit for decoding the universe. We're going to look at how physicists literally hacked the rules of reality using incredibly strict definitions to unlock the greatest mysteries of the cosmos. It all starts with one seemingly simple question. How do we actually measure the universe? Think about it. We can theorize about black holes and quantum mechanics and the birth of stars all day long. But if our fundamental measurements are flawed, well, our entire understanding of reality just falls apart. Measurement is the crucial bridge between human imagination and physical reality. And to cross that bridge, we need an agreed-upon language. Enter the unit. A unit is defined as a certain basic, arbitrarily chosen, internationally accepted reference standard. Without this, physics is really just throwing meaningless numbers into the void. Saying a building is 12 tall means absolutely nothing unless every single one of us agrees on exactly what that unit of measurement is. It's an arbitrary choice, sure, but it's a choice that the entire scientific world has shaken hands on. So here is our roadmap for today's explainer. First up, we'll cover the universal language. Then we'll look at the art of precision, step back to explore the dimensions of physics, and finally, we're going to do some literal equation hacking. Let's get right into it.
Starting off with Section 1, the universal language.
Think of these 7 SI-based quantities kind of like the primary colors of the universe. Just as you can mix red, blue, and yellow to paint literally any picture imaginable, you can combine length, mass, time, electric current, thermodynamic temperature, amount of substance, and luminous intensity to describe absolutely every physical phenomenon in the cosmos. Force, energy, momentum, pressure, they're all really just combinations of these 7 fundamental building blocks. It is an incredibly elegant system.
All right, moving on to Section 2, the art of precision.
And that brings us to significant figures. Now hold on, I know exactly what you might be thinking. This sounds like a bunch of boring math class trivia. But physicists don't view significant figures as busywork. Not at all. They view them as a strict system of honest reporting. See, every single measurement has some inherent error based on the instrument you used. Significant figures make sure you never overstate your scientific confidence. The golden rules are pretty strict. Non-zeros and trapped zeros always count. But the real tricky part, and the absolutely essential part, is how we handle trailing zeros. Let's look at this in action. Contrast 12,300 millimeters with 4,700 meters. With 12,300, because there's no decimal point, those trailing zeros are just holding the place. They don't actually represent precision, so that number only gives us 3 significant figures. But with 4,700 meters, the mere presence of that decimal point completely changes the game. By explicitly writing out those zeros after the decimal, the scientist is loudly declaring, "I am absolutely certain of these digits," and that gives us 4 significant figures. It's basically a brilliant, silent code for certainty.
Okay, let's put this to the test. Take a look at the number 0.002308. How many significant figures do you actually see there? Take a second. If you apply those rules of honest reporting, you'll realize the leading zeros are just placeholders. They tell us how small the number is, but they say nothing about the precision of the instrument. The non-zero digits, 2, 3, and 8, obviously count, and that 0 trapped right in the middle, it counts too. So we are left with exactly 4 reliable digits.
Now, here's where it gets absolutely crucial when we actually start doing math. Let's say you measure the mass of an object down to 4 significant figures, but you only have its volume to 2. If you calculate the density by dividing them, your calculator might spit out a crazy number with 11 decimal places. But mathematically speaking, a calculated result cannot magically be more accurate than your clunkiest original measurement. You have to identify the input with the least precision, in this case the volume with 2 figures, and brutally round your final answer to match it. A chain of scientific data is only ever as strong as its weakest link. And speaking of rounding, physicists use this bizarre but completely essential rule. When you're rounding off a trailing 5, which way do you go? Most of us were probably taught to just always round up, right? But notice here that 2.745 rounds down to 2.74 because the preceding digit is even. But 2.735 rounds up to 2.74 because the preceding digit is odd. Why do we do this? Well, if you're crunching millions of data points and you literally always round 5s up, you're going to create a creeping statistical bias that artificially inflates your results. The even/odd rule perfectly splits the difference. It rounds up half the time and down half the time, keeping the entire universe in mathematical balance. Which brings us to Section 3, the dimensions of physics. When we're operating in the realm of mechanics, you can basically strip away all the complex units and numbers entirely, and what you're left with are just 3 fundamental dimensions: mass, length, and time. Every single mechanical concept you can possibly imagine is really just an arrangement of these 3 things. Let's see how this actually builds. Take velocity. It doesn't matter if it's meters per second or miles per hour, its fundamental dimension is simply length divided by time, or LT to the -1. Acceleration is velocity divided by time again, so its underlying DNA is LT to the -2. You see, dimensions completely ignore magnitudes. They really don't care if you're measuring a crawling snail or a rocket ship. They only care about the fundamental nature of the physical quantity itself. All right, Section 4. This is where it gets really fun. Equation hacking, also known as dimensional analysis. We can literally use dimensions to interrogate the universe itself. Take the extremely famous formula for kinetic energy. K equals 1/2 mv squared. It looks incredibly elegant on paper, but how do we actually know it's mathematically sound without running a single physical experiment? Well, we test its dimensional consistency. Check this out. On the left side of our equation, the known dimensional DNA for energy is mass times length squared times time to the -2. Now, let's build out the right side. We just drop the 1/2 completely because pure numbers don't have dimensions. Mass gives us m, velocity gives us LT to the -1, and because that velocity is squared, we square those dimensions. When you multiply it all out, the right side becomes exactly ml squared t to the -2. The left side perfectly matches the right side. We have just proven the equation is dimensionally homogeneous. But you've got to respect the absolute power of this homogeneity principle. As the rule goes, a dimensionally correct equation need not be actually an exact equation, but a dimensionally wrong equation must be wrong. If you spend 10 years deriving a brand new theory of physics, and at the very end your dimensions for force somehow equal the dimensions for temperature, your theory is mathematically dead on arrival. It is literally the universe's ultimate spell checker. And we can take this one step further. We can actually use this cheat code to invent formulas entirely from scratch. Look at these steps for deducing a pendulum's period. Step 1, we assume the time it takes to swing depends on its length, gravity, and the mass of the bob. Step 2, we write an equation setting time equal to those variables, raised to unknown powers x, y, and z. Step 3, we equate the m, l, and t dimensions on both sides, and through some really simple algebra, we discovered that the mass dimension actually cancels out completely, meaning the weight of a pendulum doesn't affect its swing at all. We solve the remaining exponents to discover that time equals a constant times the square root of length over gravity. We just hacked the mathematical relationship of a pendulum without ever touching a single piece of lab equipment. How cool is that? As we wrap up this explainer, I really want to leave you with a bit of a provocative question to think about. How do these incredibly rigid rules of measurement actually give us the ultimate freedom to discover the universe? Today, we've seen that defining units, obsessing over trailing zeros, and balancing dimensional brackets, they aren't just dry academic exercises. This toolkit of strict, unyielding rules is exactly what empowers us to accurately decode the physical world. It strips away our biases and reveals the brilliant underlying machinery of reality itself. So keep questioning, keep analyzing, and I'll catch you in the next explainer.